Alright, so what I wanted to do with this video is give you guys a quick walkthrough of what we were discussing after we had gone over the Unit 2 exam. We started looking at the Unit 3 unit packet, going through some of the new content that we had there, and I didn't want folks who were making up the Unit 2 exam because they were taking it late or had been absent, whatever was going on. I wanted to make sure we all started this particular unit on the right foot and wanted to do one additional practice problem before I set you guys loose to work on the homework for Friday, which is really only like 5 questions. So the first thing I wanted to do, actually, is talk briefly about your cover page for this particular unit packet. Let me zoom in here a little bit. Obviously, as always, you'll be able to see the unit objectives. You'll notice we've got brand new equations. And they look kind of complicated and kind of scary, so I want to walk you through where you can find all the information you're going to need for them, show you where we get these equations from, and then at least apply 1 or 2 of them to a few of the problems that were in the homework. It should take, I don't know, maybe 10-15 minutes. So I won't get into nearly as much detail as I did in class. This is just the quick edition for those of you who guys weren't here. Again, unit objectives are there, so that's a good list of things to make sure you can do for the exam. With our first couple of units, students often get complacent, thinking that it's going to be relatively straightforward content. We're just talking about speed, blah, blah, blah. There's not a lot that you can do there. And then when they take the exam, they realize, well, there might have been a little bit more that we discussed in class that showed up on the exam than they might have thought. So those are the objectives. It's a really good thing to go back and double check. Obviously, we have our calendar for the entire unit, when things are going to be due by, what we're doing each day. And then down here, you'll notice really the only thing that we're adding. And yes, it leads us to literally three new equations, but the only thing we're adding is one new variable, one new term, and that's going to be acceleration. So acceleration going to be defined as the rate of change of velocity. Ultimately, what it comes down to is us being able to, let me go back to doing this, take a look at our graphs. So in the previous unit, when I had said, hey, this is where we get the speed equation, it shouldn't be brand new stuff. Or it shouldn't be, I shouldn't say brand new, it shouldn't be a mystery where we get the equation from, right? We had a distance versus time graph. The slope of that line, be it positive, negative, 0, whatever it was going to be. The slope of that line from our same equation that you were taught in your algebra or geometry class is your change in y over change in x. In this particular case, my y-axis contains my distance. My x-axis contains time, because that's what's plotted on those 2 parts, and then my slope becomes my velocity. And this was the equation we used in the entirety of what we were working on over the course of the last, 2 weeks at least. So that's where this equation came from. Now we can do the same sort of thing, right? If I've got a line that starts right here, travels horizontally for a little bit till we reach this particular position, and then goes up and at an angle. What I've represented here is one slope of 0 and then another slope. Let's just come up with a random number and call it 2, right? It's greater than 1, it's positive. It's going up and to the right. We'll just say it's a slope of 2. So that's a change, not just in your slope, but that's a change in your velocity. And anytime you're going to have a change in velocity, you're going to be talking about an acceleration. This particular change would be instantaneous, which isn't what normally happens. Normally, when you're going to change a velocity, let me get back to something clear that I can work with. When you're changing velocity, you don't, like from a stop sign, go immediately from traveling at 0 meters per second or 0 miles per hour to, in the next instant of time, doing 20 miles an hour, right? You gradually speed up. You change your speed to 10, 5, 10, 15, 20, 30, whatever. And you get this curve, right? You gradually get up to whatever speed you want to. Once you achieve that speed, then, you can continue on your merry way, not pushing the gas pedal nearly as much as you had been. So curves on a graph are a little complicated to understand, so we can go a level up, basically, and talk about a little bit more complicated sort of graph, a velocity versus time graph. If we look at a velocity versus time graph, everything on the y-axis here describes what speed it is you're traveling at. So if you're not moving anywhere, 0 on a velocity versus time graph would literally be 0 meters per second, not going somewhere, would literally be at 0, horizontal line at 0, and it stays that speed the entire time. If you start with a y-intercept, let's say, of 10, let me erase that velocity. It's a little bit big. I'll move it elsewhere. We'll move it up here. But if you start with a velocity, let's say, of 10 on your y-axis, that doesn't mean you're starting 10 meters away. It means when you start recording time at t equals 0, you have a velocity of 10 meters per second, miles per hour, whatever it is. If it's a flat line, it means you're maintaining 10 miles an hour, 10 meters per second. And if that line changes, that means that you're gaining speed or losing speed. And so that's going to be a little bit different. We'll talk about it more in class, naturally. But the reason I bring it up is because we use the same idea, and it's the equation of slope in order to get our equation for acceleration. In fact, it's the first equation. If I come back over here to our unit packet, it's the first equation you see written up here under the section new key equations. The first equation you're going to see written is change in velocity divided by change in velocity divided by time. And you'll notice from this particular equation, from slope, from our graph that we see over here with velocity versus time, we're going to have a change in velocity in our y-axis, right? Your speed is going up, your speed is going down, your velocity is somehow changing, divided by our value of time, and this is what we give our term acceleration to. Now, just like from the reading notes quiz or the last unit exam that we took, you can rewrite this particular equation in multiple ways, right? We can, instead of using that triangle, if the Greek letter delta scares you, you can rewrite it as VF minus VI, just like we did in Unit 1 with time, and in our most recent unit with your distances, right? It was on the reading note quiz for sure. That little triangle literally just means whatever its final value is subtracted from its initial value. We're going to use that quite a bit, but it's still going to be divided by time. The next thing I wanted to show you was the second equation that we use directly beneath that. The second bullet point on the page to my right isn't really a new equation. All I did was basically look at this fraction, VF minus VI over t, and recognize that I don't like fractions. So if we get rid of that fraction, we can multiply both sides by time, get time on the right-hand side, then we wind up with VF minus VI, and you'll recognize that if we want to solve this, yeah, there it is. If I want to solve this for my final velocity, then I add velocity, initial velocity, to both sides. I would wind up getting VI plus AT is equal to VF, which is the exact same thing you see on the other side of the screen, just flipped. So this equation for acceleration, just like the equation for velocity, comes explicitly from the graph. These aren't things that people made up because they wanted to make the lives of physics students in the future difficult. These are all of them coming from the equations. We could even look at the equation we've got down here for VF equals VI plus AT, and we could rewrite it in terms of m, x, and y still, right? Our y1 value, or initial velocity, is y1 plus our slope, which was a, the letter A. Our time was our x-axis, and then this is y2. So all of them still fit this mold of our linear relationship that we have inside this graph. We're just being specific about what value is on our y-axis, and we're being specific about what value is on our x-axis. If recognizing, and again, the only point of this conversation right now is so that you can see clearly that these two equations, these two bullet points, are the same equation. I didn't change anything. I just rewrote it in a slightly different way, just like I did with the velocity equation in the last unit. If seeing all these subscripts is throwing you off a little bit, I want to reference the fact that I include exactly what those subscripts mean down below. Anytime you see a subscript of an F underneath it, it means we're talking about the final value for that measurement. In this particular case, it's velocity. So the capital V, because it's still a velocity, we just need F and I to differentiate where you end, the final velocity, from where you started, the initial velocity. Sometimes there'll be non-zero numbers, sometimes one of them will be zero, but it is important. And so that's where we got that particular equation from. If you would like to see it, the textbook walks you through the derivations for the next two equations. In class, when I had a little bit more time, I did do the derivation for the last one because that's, in my opinion, the scariest looking one. But also, rather straightforward, rather easy in order to explain, where we got that. But I'm going to skip over that for now. If you're interested, it is in the book, or you can just ask me and I can walk you through it a little bit later on. My point behind showing you where these equations come from is to always provide evidence, right? That's one of my big pet peeves is even if I ever make a claim, anyone makes a claim in your life, they've got to be able to back it up with some evidence. And so this is where these equations come from. This is me showing you where they are at. I'm not going to require you to actually be able to show me where we got these equations on a test, on a quiz, or really ever again. I just wanted to be able to show you exactly where they came from. So let me scroll down a little bit, and I'm going to keep working on this little workspace that I've got over onto the right-hand side. First thing I'm going to do is for Unit 3, Assignment 1, this was the notes that we worked on together in class today. We didn't get very far, so I wanted to add a little bit for those of you who were there in class with me. Just to help clarify a few things. But I'm going to start with number 1, and I'm going to walk through all of the exact same steps that you guys should be following as well when you go to solve any problem in physics, but especially now. Last unit we only had one equation. Now we've got the one equation from last unit plus 3 more equations that we could potentially use, and so it's going to be really important for me, not only if I am to assign you extra or partial credit, but also for you in order to see where it is you're headed with a problem. Go back and check your own work. Maybe you'll spot your own mistakes, sort of thing. Following these steps really just kind of helps everyone involved in the entire process. Helps you think through everything. So first thing you're going to do is go through and label all the variables that are provided. Car accelerates from 0 to 30 meters per second. Well, meters per second will always, always, always describe a velocity. So I've got 2 velocities provided here. One of those velocities is 0 meters per second. The other velocity is 30 meters per second. Now it's important to recognize which one is your final and your initial. Where does this car begin accelerating, and what speed does it have when it ends accelerating? And so the way it phrased it here, it goes from 0 to 30. So my initial speed, where it starts at the beginning of the problem, is 0. This could also be phrased as starting at rest. That would mean the same thing. And then there's your final velocity of 30 meters per second. The time was then provided next. It was 3.5 seconds, right? 3.5 isn't a distance. It's not a speed. It's literally just a time. And then in letter A, they ask me for acceleration. I always like to put a little question mark there. When we get to it, I'm going to show you how the units work out and everything here in a second. I would also encourage you guys to put the units for acceleration there. If you write down exactly what units your answer should have, like if I asked you how long it would take this car to accelerate from 0 to 30 meters per second, and your answer comes out to be 3.5 seconds, but you fumble the math to get there, but you still recognize, hey, my unit of time in this speed was seconds, so my answer should come out to be in seconds, then that's worth half a point, right? Just clearly identifying exactly what your answer should have been measured in is a valuable piece of information. So let's calculate this acceleration. The first thing I'm going to look at are the equations that were provided on the front of the unit packet. The first thing I would do, honestly, is I would go into here and start. Let me erase that. I want the eraser. There we go. First thing I would do is I would go into this page and take all of those little bullet points, right? The first 2 equations are the same. The first 2 bullet points, I should say, are the same equation. But I would take at least those 3 bullet points, unique ones, and add them to my equation card. That would be the first thing that I would do. That way you've got that next to you, your equation card's updated, you're not scrambling to do that last second for the exam, right? You've got it all there and you're used to finding things on it, so it becomes almost routine just to help things move along next exam that we take. So I've got an initial velocity, a final velocity, a time, and an acceleration. I need to pick an equation that uses all of those variables that I have present in order to help me. Oftentimes one of the things I'll see students do, because you're comfortable with it, right? It's kind of like my daughter's teddy bear that she might sleep with, right? A lot of us will try and jump back to the equation v is equal to d divided by t, right? Velocity is equal to distance divided by time. We can't use that equation for 2 reasons. First reason, number 1, it asks us to use and or we're solving for distance. Nowhere in 1A does it say anything about distance. It doesn't provide a distance. It doesn't ask me for a distance, so I'm not going to use an equation that contains a distance. That also means if I look over here at the other equations I had available to me, I'm not going to use my 3rd or 4th equation on that list of new equations because they also contain the value for distance. So far in 1A for assignment 3 or unit 3 assignment 1, no mention of distance has been provided at all. So we're going to ignore it completely. Don't try and make up something for distance. Yes, you could solve for distance, but that would give you an extra problem you've got to solve before you can then turn around and find acceleration, and that would make it significantly more complicated, and let's not do that, right? The other reason you shouldn't use the original equation that we had in our last unit is because there's only one velocity there. Do you plug in 0? Do you plug in 30? You're going to need to have two spaces for velocity. So because we're solving for acceleration, we need to use one of the new equations that are on the unit packet. But then the other thing that I notice is I'm solving for A. This equation right up here is already rearranged to solve for my acceleration, whereas this one has acceleration in a term with time. So if I use the second bullet point, I would have to move the initial velocity to the left by subtracting, and then I would have to divide both sides by my time. That's a lot of work. Let's just go ahead and use the equation right here that has everything rearranged for me as I already would need it. So I've got acceleration is equal to VF minus VI divided by time. When you're showing your work, let me know which version of the equation you picked. So write out the full equation. Now we're going to go in and we're going to plug in all of our numbers. Here we're going to have 30. Again, it's meters per second. I'll explain why I'm doing this in a second. Subtracted from 0, all divided by 3.5 seconds. First thing I want you to notice is it seems kind of silly to write down minus 0 meters per second. Obviously, 30 minus 0 is still going to be 0. I'm including it here because oftentimes in these problems you will not have an initial velocity of 0, and I don't want us to get in the habit of just ignoring the second velocity. So even if you're just writing minus 0, it's a good habit to get in. The other thing that would be important is if the final and initial velocities flipped. Right? If your initial velocity was 30 and your final velocity was a 0, then you would flip them. It'd be 0 minus 30, and that negative 30 from the subtraction sign is really important. So my acceleration here is going to work out to be, I think the answer key had it at 8.56? Let me look it up. Because remember, just like all things, I give you guys the answer key. Let's go to the end of the worksheet. Number 1, 8.6 meters per second squared. I'll explain where we got the meters per second squared in a second. But 30 minus 0 gives us 30. Naturally, we're going to divide that by 3.5 seconds, and we get 8.6. Now my units, this is where it's going to be important. We've got units of meters per second already up top in my numerator still, and then I've got an additional unit of seconds down below. So we can report your units for acceleration as 8.6 meters per second, or as I will traditionally write it, you can write it out as 8.6 meters per second squared. That's how I would have reported this answer. Technically, meters per second is not wrong, and if I'm typing up a quiz or I'm typing something up in some sort of text format that doesn't allow exponents easily, as you guys might for maybe a lab report or something like that, then I would just do divided by a second, divided by a second. Don't worry about trying to find that squared button. Just divide it by a second again, and that's your unit of acceleration. What this means is that with every second of time that passes, this car increases its speed by 8.6 meters per second. So after 2 seconds, it would be, what, 8 would be 16, 17.2 meters per second in your second. In your third second, you add another 8.6, so on and so forth. So that would be how I approach 1A. 1B, once you know what this acceleration is, you can actually go ahead and just include that acceleration in your list of variables, meters per second squared. Now we're looking for distance. This was 1A. Now we're going to go through and actually solve for our distance in 1B, at which point it really doesn't matter which equation it is you're going to pick from the worksheet. So if you go back to that equation, the box of equations, you could use your third bullet point or your fourth bullet point, your third equation or your fourth equation presented to you, and either one technically would be correct. In class, I showed everyone both of them. I'm just going to pick one for now. So if we use VF squared is equal to VI squared plus 2AD, right? We've got your final velocity squared. It is equal to your initial velocity squared plus 2 multiplied by your acceleration multiplied by your distance. This is the equation that I would pick because it seems a little bit less intimidating than the 1/2 AT squared shenanigans that we have in the fourth one. But again, same rules apply. Show me what equation it was you're trying to use so I can get you partial credit in case we miss a step or something goes wrong. But then plug in everything in the correct spot. You've got 30 squared is equal to 0 squared plus 2 multiplied by 8.6 multiplied by your distance. In this particular case, 30 squared is 900. That's going to be equal, obviously, to 0. But then your 8.6, when you simplify what's going on over here, which you can totally do. Sometimes I'll just sit here and I'll divide by 2 and then divide by 8.6. But you can also simplify the 2 and the 8.6. You'll get 17.2 multiplied by your distance. Then you can divide both sides by 17.2. And you should get a distance of approximately, if my rounding is correct, we'll divide both sides by 17.2. You should get around 53 meters as your distance. Now you could go in and use the other equation in order to solve for this. I want to point out there was a number in what I wrote here that I did not include. I did not include 3.5. 3.5 wasn't, I didn't decide not to include my 3.5 seconds because I didn't like 3.5 seconds as a measurement. It's not because I don't like decimals. 8.6 is also a decimal. There's no rationale behind it other than the equation here, VF squared equals VI squared plus 2AD, does not contain time. Common mistake that I'll see is people just assume that because it's something provided to you, you have to force it into one of these equations, and you don't have to in any way, shape, or form. That equation didn't call for time, so I'm not going to use it. The other thing that I want to point out is if we go back to that cover page and you look at your last equation at the bottom of the page, this particular, come on, let me erase. I don't know why it won't let me erase. Anyways, this particular equation right here does not include final velocity. So nowhere in this equation, if I had used this for 1b, would I use 30, right? It would be 0. Your initial distance, you can always... I think I took out all of the problems, if I'm being completely honest, that contain some sort of initial position. If you start measuring where you're at the beginning of the problem as 0, and you make it the origin on your xy axis, then you don't have to worry about that initial position term in your math problem. And it makes everything a lot easier. But your initial velocity is 0, multiplied by any value of time is still going to be 0, and then really all you've got left is your 1/2 AT squared. That's all you would have to worry about. So, it doesn't matter which equation it is you select, so long as you plug in the terms in the correct spot. And this is why making that list of variables is so important. It tells you what you've got, kind of like a list of ingredients, and then the equation is your recipe, and it tells you how to put it together. Really bad analogy, because this is clearly not cooking. Food is significantly better than physics homework, but it does work. So we're going to skip 1C and 1D. Not really all that important. I can talk about them a little bit later. The answers are provided. It's really just a vector thing. If you start with 300 meters and you're moving forward or away, how would you add or subtract that 53? That's all that was. Number 2. This is something that I want to talk about in some detail. There's a couple things going on with number 2. Let me get a fresh clipboard. Can I do that easily? Let's find out. New. No, I don't want to save that. Okay, awesome. So, got myself a fresh little clipboard. A bowling ball is dropped from the roof. Anytime you see the word dropped, right? If you're dropping something, I want you to pick something up. Maybe take your pencil, hold it a couple of inches above the table, and let go of it, right? If you drop it, you're not throwing it down at the table. You're not throwing it up into the air. You're not throwing it right, left, forward, backwards, or any of the other combinations of directions that something could be thrown. You're not applying any velocity to it at the beginning of its motion. You're literally letting go of it, letting gravity take hold of it, and pull it down to the ground. We'll talk about why gravity does that later, but you're letting gravity pull it down to the ground. So one thing you'll always know, if you ever see the word dropped in any of these problems, you'll know right off the bat that your initial velocity should be 0 meters per second. That's always going to be the case. It's never going to change. The other thing you're going to know right off the bat, and this is something that I will actually demonstrate to you guys in class on either Friday or Monday, depending on when I see you for the lab. The lab itself, if I'm doing the procedures, should take maybe 10 minutes for us to collect all of the data, so I wanted to do a few other things that day, and one of them is going to be to show you experimentally that the acceleration due to gravity on the Earth is always, always, always 10 meters per second squared. Notice this is meters per second squared. I even wrote the word acceleration next to it. I understand meters per second versus meters per second squared seems like a ridiculous difference, and a lot of us will stare at meters per second squared and initially think that, oh, hey, this is a speed, this is a velocity. It's not. If you have that second squared at the end of it, that means for every second of time, you're going to have a change in speed. Just like for every second of time in a velocity, you have a change in position. For every second in time, you have a change in speed. Your meters per second change. So it's one level up in terms of complication, I guess you could say. So these are two things that you know right off the bat. If you're on Earth, gravity is 10, and if you're dropping something, your initial velocity is going to be 0. We're going to use that for the remainder of the worksheet. So what I'm asking you to do in letter A is calculate the final velocity of this object. Don't know what that's going to be. It's probably going to be measured in meters per second because those are the units that you see in all of the other values that are provided. Why make this in miles per hour and then have to do a ridiculous unit conversion? That's silly. If you're measuring this at the end of 1 second, 2 seconds, 3 seconds, and 4 seconds, we're going to have to do this problem 4 times. I would never give you a test question where you have to do this 4 times, but I would definitely give you a test question where you have to do this once for sure. So time is equal to 1 second. I'm going to start right here. I have time, I have the final velocity is what I'm searching for, acceleration, and distance. I don't know, or sorry, and initial velocity. I don't know anything about distance, so I am literally picking the one equation on the front of my unit packet that does not contain the letter D. Those first 2 bullet points technically are the same equation. I chose this one because it's already rearranged to solve for my final velocity. Why reinvent the wheel? So this makes all the math really easy. If I'm looking for that final velocity, your initial velocity was 0. We've got 10 as my acceleration due to gravity, and then it's falling for 1 second. As it falls for 1 second, you'll notice, right? It doesn't take that very complicated of mathematical skills to recognize that this is still just going to be 10 meters per second. So after 1 second of falling, this object, whatever the object is, if it falls for that full 1 second, will be ending that 1 second with a new speed of 10 meters per second. We can do the exact same thing at 2 seconds. So if my velocity, my velocity is what I'm looking for after 2 seconds. The initial speed, because I'm still dropping it, is still going to be 0. The acceleration is 10 meters per second squared multiplied by 2 seconds. And then that's going to give me 20 meters per second. You might notice a pattern, you might notice a trend. At 3 seconds, your final velocity is going to be 30 meters per second because every single second you are traveling 10 meters per second faster than you had been the second prior to that. Now, eventually in the real world, you've got something like air resistance. Drag is the official term for it. You've also got the idea of terminal velocity, which we'll talk about when we get to forces. That one's actually a really, really cool idea, but not idea, it's a phenomenon. It's just what happens. In this particular case, with generic acceleration, we'll talk about, ignoring air resistance and things like that, you're going to be gaining 10 meters per second every second you're falling. That might not seem like much, but if we converted that to miles per hour, it's about, 22 to 23 miles per hour you gain in speed every second of free fall. So after 1 second of free fall, you're going around 23 miles an hour. After 2 seconds of free fall, you're going around 46 miles per hour, which is just astronomically fast, right? It's faster than almost all of the cars that are commercially available out there in the world. There might be something that can do 0 to 60 in under 4 seconds. Probably is at this point, but it's not going to be something everyone owns. So this is very, very, very quick. This is the way gravity itself is going to be working. We're not going to bother with 2B or 2C. I will walk through those more in class when we're together. That's not part of the homework. I do want to move on just for the sake of time for this particular video to number 3 so that you guys can have that walkthrough, because I want you to do something similar in 4, 5, 6, 7, and 8. So for this particular page, let's get myself a new one just to clean it up a little bit. So in this particular page, we've got a seagull that's dropping. Again, I see that word drop, so the first thing I'm thinking of is with the word drop, that means my initial velocity is 0 meters per second, and my acceleration is going to be 10 meters per second squared. I don't know about you, but I don't have any evidence to confirm that seagulls exist elsewhere in the universe. So if we're talking about a seagull, we're probably on the Earth. So I can assume gravity is going to be 10. And again, I'll demonstrate that in class Friday or Monday, whenever I see you next after we have this conversation. So in this case, the only other bit of information that is provided in number 3 is going to be 100 meters. It's 100 meters above the beach. So sometimes you could draw a picture, right? I'm not very good at being an artist. I think my 7th grade art teacher is still very disappointed in me. So if this bird drops this rock, I'm just going to draw the rock. I'm not going to attempt to draw the bird. And it falls. It's going to fall in a downward direction. We'll talk more about direction later. That is going to be important, so don't think I'm ignoring it. I just want you to get the basics. Your distance that this object is going to fall is 100 meters. Right, from here, from what would officially be the origin, all the way down 100 meters. That'll be important later. So the distance is 100 meters. They don't give me any other information here in number 3. Notice there are 2 things that I can assume, and then there's 1 thing that they gave me. Letter A asks, what is the downward velocity of the stone the instant it left the beak of the seagull? We already answered that, actually. So if we want to look at 3A, the instant it left, the bird didn't throw it down at the ground. The bird didn't throw it up in the air. Your initial velocity is going to be 0 meters per second, because it's simply letting go of it, letting gravity do its thing. That'll be the same case for anything that's ever dropped, ever. We will get to the point where we talk about things being thrown up in the air or thrown down at the ground, but we're not there yet. How long does it take, letter B, for the stone to hit the ground? If they're asking how long does it take for the stone to hit the ground, they're asking me about time. Now, look at all of the things I've written so far in my list of givens or in 3A. The only unit of time that is present is seconds. So I know right off the bat, regardless of how things cancel out in this problem, my time's not going to arbitrarily and randomly come out in hours. It's going to come out in seconds. So I've got to be careful with that. The equation that I'm going to use, because I have VI, A, D, and T, I don't know anything about its final speed before it hits the ground. Yeah, we could maybe try and figure out letter C first, but you'll notice that one even literally just stops at 2.5 seconds. It's not the full problem, so it might not be the full amount of time. So we've got to find out how long it's going to take without knowing anything about the final velocity. And if you go back to the list of equations provided on the front of the unit packet, there is only one equation that doesn't contain final velocity. And that equation is, in all of its glory, df is equal to di plus vi t plus 1/2 at squared. Please don't panic and think, oh man, I've got x and x squared, right? T and t squared in separate terms. This is a quadratic. I've got to use the quadratic equation. All of my years of teaching physics, I've never needed to use the quadratic formula in order to solve one of these things, because usually physics teachers are kind of nice, and we always allow the object to start at rest, especially when we're doing one of these drop problems. So the object is going to start at rest. There are 2 things that we know right off the bat. I think it's silly to assign any displacement for where we're starting, right, where the rock or the object that the seagull is dropping begins at. I think we should just set this right at 0 meters. That's my origin. That is 0, and if that's 0, then that means my initial displacement can also be 0. And I just get to skip that term entirely. I'm pretty sure I took out all problems where that's not the case. If I didn't, it's one random problem, buried deep within one random homework assignment. It's definitely not on a quiz or on a test. The other thing that I do know to be 0, though, that is going to help me when I go to plug all of this in, is my initial velocity. So I'm going to plug in what I do know. I know that I fell down 100 meters, right? I was displaced 100 meters from where I started, which is why I knew that was my final velocity, or my final distance, sorry. Then I've also got my initial velocity, which I've already talked about at length at being 0, time is what I'm solving for, so that's a variable I'm going to leave alone. And then I've got 1/2 of 10 multiplied by t squared. I'm going to put the square in parentheses to remind you that it's only time that's being squared. We're not squaring the 10, we're not squaring the 1/2, only time is getting squared. So you'll notice this entire term right here at the front can disappear because your initial velocity was 0. You get 100 meters is equal to 1/2 of 10 multiplied by t squared. I'm going to put these back here because it bugs me without them being there. Sorry. Anyways, so you've got a couple of options now that we've simplified and made this equation a lot easier to look at, right? It's just more appealing. There's fewer terms. There's less complication here. Next thing I would do is I'd actually simplify the 1/2 and the 10. So I'd leave 100 where it is. It's equal to 5t squared. We've got to get t by itself. Undo reverse order of operations. Move 5 first. You undo that multiplication and division before you ever touch any exponents or anything else. And so what you should notice, let me get my cursor found again so I can scroll down, is that you're going to get 20 is equal to t squared. We're not done. Take the square root of both sides, and your time should work out to be, I believe it was 4.4 seconds. That is how long it took the object to hit the ground. This equation got really easy because, first and foremost, your initial distance we can almost always assume is 0. The book included it, which is why I wrote the equation this way. It comes straight from the book. You'll be able to find it in there, where they also derive that equation for you again in case you were upset that you missed out on that part of our little talk in class. The other part that disappeared was your initial velocity, that whole term. It doesn't matter how long this thing is falling for. If your initial speed is 0, then your initial speed multiplied by how long it fell for will always still equal 0. Right? 0 multiplied by infinity is still 0. So that whole first term disappeared, and the equation got a lot easier to deal with. Last part, letter C. We do know how long it was falling for. This is 3C. But you'll notice in letter C, I'm not interested in its velocity as it hit the ground. If I was interested in the velocity the rock had as it hit the ground, then I would use a time of 4.4. But in letter C, they're asking me about its velocity after it fell for 2.5 seconds. So I'm going to remake my list of variables that I'm aware of. My initial velocity is 0 meters per second. My acceleration due to gravity is 10 meters per second squared. And my time of free fall that they're interested in here is 2.5 seconds. They want to know what the velocity of this rock is after it has fallen 2.5 seconds. And this gets back to exactly what I just went over in number 2A, number 2, letter A. We don't have distance anywhere in this particular part of the problem. Now, I do know how far it fell from the seagull to the ground. It took 4.4 seconds to cover those 100 meters, but it does not travel 100 meters in 2.5 seconds. It traveled 100 meters in 4.5 seconds, not 2.5. So I don't know its position above the ground at 2.5 seconds, therefore I can't use distance. If you look back at that list of equations that are on the front of your unit packet, only one equation does not contain distance, and there's a version of it that is rearranged to solve for VF already. It's my favorite one. VF equals VI plus AT. This equation we can use here. VF is what we're solving for. VI was still 0, and this looks identical to what we just did in number 2, letter A. The only difference is that instead of using 1 second, 2 seconds, 3 seconds, and 4 seconds, we have 2.5 seconds. But guess what? It's still the same thing. If you want to know how fast an object is moving as it's falling, take its time of fall and multiply it by gravity. Multiply it by 10. So your final velocity here is going to be 25 meters per second. And that's all that needed to be. So, a couple key takeaways. First takeaway, make that list of variables. If you're not making that list of variables, then identifying where these numbers should go in the equation is going to be very difficult. It's also going to be very difficult to make sure you pick the correct equation to use. For example, in 3C, had I not recognized that I didn't know how far the object fell in those 2.5 seconds, I might have tried to use an equation that contained distance and maybe accidentally plugged in 100 where it shouldn't have been, or 4.4 where it shouldn't have been. Notice those aren't in here at all. So the problems for the homework, for those of you who missed this particular day in class. The problems for the homework, while we have a lot in assignment number 1 that we can talk about, and I will as we progress throughout the remainder of the week, what I want you to do for homework is 4, 5, and 6. Number 5 doesn't even include any math. Number 6 doesn't include any math either. So number 4, we got another drop problem, very similar to the seagull. She's diving off the cliff. Just assume she starts with an initial vertical velocity of 0, because they don't give you a velocity otherwise. She's just running over the edge and doesn't jump up or down. She just goes over. And then I want you to also work on 7 and 8. 9 you could do. Totally, I get that. Number 10 you could do, and we'll talk about them in class vaguely. I just want you to get the practice with those 3 math problems, 4, 7, and 8, of making lists of the givens that you've been provided, picking the correct equation. So really it's 3 math problems and 2 conceptual problems that I'm asking you to do for your homework. When is that homework due? Real quick, let's take a look back at our unit cover page. You'll notice that Unit 3 Assignment 1 is going to be due Friday at midnight for everyone. The other thing you'll notice is Thursday at 11:45, close to midnight, but quizzes won't let me do 11:59 p.m., so I'm making it the last option for submitting it through that site that I could. You got your pre-lab as well for lab number 1. You'll find all the materials you need for lab number 1 for the pre-lab, the digital version of that document on Teams. It's up there, obviously titled Unit 3, Lab 1. But then the other thing you'll also recognize is, or will have available to you, is I'll print a copy of that for class. So don't feel like you have to print it yourself. Just use the digital version to help you with the pre-lab on Quizzes. It's ready to go. Start taking that now if you can. And then I will have a paper copy for you when you walk in the door for the day of the lab. There's really not a whole lot left that we talked about in class. Everyone has to be in class on the 14th for the PSAT, SAT day, at least juniors and, I think it was juniors and seniors, juniors and sophomores, one of them. Juniors, you got to be there. I know that. And then from there, you'll notice there's a couple of other quizzes that were labeled and listed on here as well. So I encourage you guys, take a look at that calendar, make some notes, highlight some stuff, whatever it is you got to do. The last thing I would mention, and this is something that I know a lot of us didn't look at before this test, is on the top of the second page, there's that common mistakes with this particular unit. I made these lists, and these are on all the unit packets, after grading the exams. While it was fresh in my mind, every year I go back and I update this list based on, oh, hey, this group had a lot of questions about this, and I'll add a bullet point or take a bullet point away if I got better at addressing that, right? I'm doing this partially so I can get better at my job, but then also so that you guys have a place to come to in case you're getting stumped on something, in case you want something to review for the test. Not only are there obviously review guides at the end of every single unit packet, I've got the supplemental packets that are on Teams as well that you could try if you want extra practice, but this list is really, really going to be a good one to come back to time and time and time again. But that was about it. That catches you up with everything that we talked about if you were taking the exam during the following day because you missed or you were out or whatever was going on, even if you just wanted an extra place to hear that same spiel again. So let me know if you have questions, comments, concerns, and I'd be happy to help you out.